Hello everyone, my name is Yaliu. I'm from Qihoo 360. My talk name is Lightweight Emulation-based IoC extraction for Gafgyt botnets. This is the outline. Firstly, I will introduce some background about Gafgyt botnet and lightweight emulation. Secondly, I will introduce the Gafgyt C2 loop, including its patterns and recognition. Thirdly, I will introduce how to lightweight emulate the interconnect function to get the wanted C2 information. Finally, I will introduce how to analyze Gafgyt variants with Mirai code borrowed with Mirai characteristic configurations. Gafgyt firstly emerged in 2014. It's also known as Qbot, BASHLITE, and lizard stressor. And before Mirai, Gafgyt was the main IoT bot family. And it used IoC-like protocol for C2 communication. Both the register and the command message are in plain text. In the past years, we have seen a proliferation of Gafgyt variants. This can be partly explained by the fact that both Gafgyt and Mirai have been source-leaked. And furthermore, there are dozens of open-source IoT exploits in the wild. All those factors make developing a new Gafgyt variant very easy. It just becomes a process of code copy and paste. While there are so many variants, according to our data, most of Gafgyt C2 servers only kept active for a few days. And that can be well observed from the variant of vbot. This variant kept active from middle April to middle June. In total, 2 versions have been found. And during its around 6-day lifespan, as much as 31 campaigns were detected, with 572 samples captured from 12 downloader servers. From those samples, 13 C2 servers were founded. In average, each C2 server only kept active for 4.6 days. To find that sort of fast emerging while short-living threats, I think quick IoC extraction would play an important role. And current IoC extraction solutions can be divided into sandbox-based and static analysis-based. Sandbox-based solution has the following issues. The first is you have to deploy multiple CPU architectures or sandboxes because you are dealing with IoT botnets. The second is you need to pre-know the fixed patterns in C2 messages so that we can check the C2 communication from network traffic. The third is your sandboxes may potentially impact other systems due to the lots of scans initialized by the running samples. And as for the static analysis, it heavily relies on the static code signatures, so it's easy to imagine that it has the issue of signature explosion. Therefore, I propose the lightweight emulation-based IoC extraction. Basically, it's a kind of dynamic analysis technique, so I compared it with the sandbox-based solution, as shown in this table. And they both belong to the dynamic analysis technique. And sandbox deals with files such as PDF, doc, or PDF, while lightweight emulation deals with code snippet such as a function. And in sandboxes, instruction level instrumentation is usually not necessary, but it's a must in lightweight emulation. And the sandbox usually provides 4 system services to the running samples, while lightweight emulation usually don't provide those services. And as for the runtime, it usually takes a sandbox a few minutes to run a sample, while that time can be greatly reduced to a few seconds in case of lightweight emulation. And sandbox usually output behavior reports and pickups, while lightweight emulation usually outputs logs of executive instructions, CPU register values, and memory snapshots. If you want to use lightweight emulation-based extraction, two prerequisites must be met. The first is fixed behavior patterns can be concluded from the interest code. In case of C2 IoC extraction, that code refers to C2 combination code. The second is that the target code can be located in an automatic manner. That is for consideration of automation and scalability. And such locating must be independent of static patterns so that we can avoid the issue of signature explosion. And usually CFG patterns are recommended. As for the emulation engine, the open source emulator of Unicorn is strongly recommended because it supports multiple architectures of CPU, which is very useful in dealing with IoT botnet samples. And it supports several programming languages, such as especially the Python, which makes it very easy to use. And it also supports fine-grained instrumentation at various levels. It's very useful in precise execution control. Next, I will talk about the Gafgyt C2 looper. If you analyze the Gafgyt main function, you can find the two loops. The second loop is responsible for building the C2 connections, registration, and command receiving. So I renamed the second loop as C2 looper. And for better demonstration, each code block is represented with two square brackets, with the first enclosing the call functions, while the second enclosing the reference to strings. Here is a summary of C2 looper. Basically, it's characteristic enough to be used to distinguish Gafgyt from other families of botnets such as Mirai. And with C2 looper, we can directly get the register message template string, which I will talk about in later slides. And we can find the init connection function for later emulation because that function is responsible for establishing the C2 connection. And the C2 looper can be found by traversing control flow graph of the main function with IDE Python or Radio 2 or whatever remote engineering tools with a graph algorithm such as deep first searching. And C2 loops also vary across variants, as shown by the blue lines. But compared with the hundreds of variants, the C2 loop type number is very small. According to my analysis, common C2 loops can be summarized into 6 types according to their CFG patterns, including the block number, the called functions, and the reference strings. Here are some example C2 loops of type 1 to type 3. And the type 1 is characterized as being composed of 4 blocks with the init connection function being called in the first block and registration occurring in the second block. And type 2 has no registration block. Type 3 is very similar to type 1, but it has a different block order in terms of connection establishment and command receiving. Here it is the C2 loop states on the analyzed over 100,000 samples. Obviously, it adheres to a long-tail distribution, with type 1 has the largest number of samples, while type 4 to type 6 are very small. As for the register message template, actually it's a kind of format control string. It is used to generate the register message. And this string changes greatly with the Gafgyt variant, as shown by the blue lines. And these strings are very useful to detect Gafgyt C2 communication from network traffic. For example, we can define IDS or IPS rules to detect Gafgyt communication in real network traffic. Therefore, template string is one of the extraction goals, and that string can be directly extracted from the C2 looper. Next, I will introduce how to lightweight emulate the init connection function to get the wanted C2 information. Here is a summarized emulation steps. It includes initialization, emulation, and post-analysis. In the initialization stage, you need to set the CPU architecture, initialize the register values, map the alpha file, including its code and data, and install these two kinds of hooks, which I will talk in later slides. And in post-analysis stage, the logged events are passed, and the C2 information is read from the sample with a passed address. Before talking about the instruction level instrumentation, I would like to analyze the most common version of init connection function, as shown by the left decompiled code. We can see that in emulation, the key is to intercept the call to string copy, so that you can get its argument of common server, and with that argument, we can further read the C2 string from the sample. Instruction level instrumentation is done through unicorn hook or hook code. It's responsible for two things. The first is when encountering a call instruction, it will log that event. Both the PC address and its arguments will be logged, and set the return value to 0 or to valid memory address. That is to make sure the execution could complete, and skip to next instruction. And when detecting ending address or address beyond the emulation range, it will stop the emulation. Memory write hooking is done through unicorn hook or hook memory write. Usually, only global memory write are useful. It's compared with stack memory write. And for each write event, the logged information includes the PC, the write address, the size, and the value, as shown by the following line. Here is a post-analysis example. The write is the logged event, and each event can be connected to the original instruction with the behavior patterns. For call event, the patterns lie in its argument. For example, for the first memory set call, it has argument 1 of a stack memory address, argument 2 of 0, and argument 3 of a constant value. And for the string copy call event, It has argument 1 of stack memory address and argument 2 of global memory address. And for the write event, the patterns lie in the write address, write size, and write value. This is another version of init connection function. You can see that the C2 IP is dynamically generated. So the key of the emulation is to intercept the call to the SC printf, and the write logged event. From the write logged event, we can connect the sprint call to the original instruction by its characteristic arguments. From the previous 2 examples, you can see that behavior patterns play an important role in IoC extraction. Here, the extraction is actually a process of applying specific patterns to the logged events, and if matched, the extraction rules will be used to get the C2 information. Therefore, I analyzed the common init connection functions and summarize them into 6 types. And for each type, I defined an extraction rule. Each rule is composed of the simplified pattern, behavior pattern, and extraction rules. The simplified pattern is for quicker matching. This is type 1 extraction rule. In the simplified pattern, the C means call, while the W4 and W2 means 4-byte and 2-byte write. Next, I will introduce how to analyze Gafgyt variants which borrow Mirai code. It's not strange that many Gafgyt variants borrow code from Mirai because they have both been source leaked and both target Linux IoC devices. And in the founder Gafgyt variant, actual Mirai code was very common. It's used in nearly all aspects of functions, including the scanning, the exploiting, and attack methods, as shown by the two figures. If you read the Mirai code, you can find a custom encrypted configuration database is heavily used. Most of the running parameters are stored there, as shown by the picture. And that database is usually copied together with the Mirai code. This may be because the original design is not better, or its connections with other modules are too tight to be easily cut, or the authors are just lazy or just don't know how to do that. Therefore, it's possible to analyze Gafgyt variants which borrow Mirai code by analyzing their configurations. As for the configuration extraction, it can be done by lightweight emulating the Mirai table init function. I have presented that topic on VB 2018 conference. If you are interested in that topic, please go to my paper. Again, I take the example of vbot. It can be used to analyze how Gafgyt variant which borrow Mirai code can be analyzed with the extract configurations. I have blocked this variant in this July. And as I said in previous slides, vbot has 2 versions. Both versions, they can be connected with the 2 similar registration code block and the same download server. And in the registration code block, we can see a very rarely seen format specifier of %f is used with sprintf to generate the message, register message, which is very uncommon in Gafgyt variants. And however, the two versions have very different configurations. And for each version, their functions can be well analyzed with the configuration items, as shown by the colored annotations. By comparing their configurations, you can quickly come to some conclusion. The first is, although they shared the same registration code, they were obviously derived from different code bases. And since the registration code is characteristic enough, both versions should have come from the same authors. And obviously, the authors have multiple sets of code bases. I also analyzed the other variants configuration. In total, 16 unique configurations have been successfully extracted from 3,700 Gafgyt samples. With the extracted configurations, those samples can be well grouped. It means each group of samples are tightly connected, and in most cases, they can be classified as the same variant. This is the most common configuration. It covers over 90% of samples. And for better demonstration, I rename it with its item count, total size, and branch name. And when comparing with other configurations, I also find some similar ones, as shown below. This is the states on other 15 configurations. The long-tail distribution hints there are lots of code copy and paste. Because more often a configuration occurs, more large number of variants, its corresponding source was used. Before ending my talk, I would like to give some conclusions on my talk. Basically, Gafgyt variants can be recognized with characteristic C2 loops. And with the C2 loops, both register message template and init connect function can be obtained. And C2 information can be got by lightweight emulating the init connect function together with the concluded behavior patterns. And Gafgyt variants which borrow Mirai code can be analyzed with Mirai characteristic configurations. That's all. If you have any questions, please contact me with the Twitter handle or the below email. Thank you for your listening.